Hi folks, welcome back to Physics with Captain Rod. This is going to be video number one of a several video series on how to draw shear moment diagrams. So what we're looking at here, imagine we've got this 6-foot beam connected rigidly to this wall as shown with a 500-pound load applied at the end. And what we're going to do, or what I'm going to do, is walk through how to derive functions for the internal shear forces developed along the beam, as well as the internal bending moments. So to start these problems, you usually begin by determining the reactions. So if I draw a free body of the entire beam here, I know that we're going to have a force exerted on the end here. So I'm going to go ahead and put a force vector here. I'm offsetting that a little bit so that we can see it. And I'm just going to call this maybe point A, so that's going to be a AY. Normally I would put an AX here, however looking at the rest of the structure there is no forces X direction, so there's no reason to apply that. So force reaction wise we're probably done. However, there would have to be some sort of couple moment applied, because you'll notice in the free body right now, if I sum moments about point A, my current free body shows a clockwise moment. So in addition to an AY, I'm going to go ahead and put a moment applied at point A. And now what I'm going to do is write equations to find A, Y, and M. So, first equation, sum of all forces, y direction equals 0, up positive, and that's going to be AY minus 500 pounds equals 0. So we get that AY is equal to 500 pounds, not a huge surprise. And we can get the moment by summing moments about point A equals 0, counterclockwise positive. So we're going to have plus the moment applied at A for this guy. This force does not provide any moment about A because its line of action goes right through A. Then looking over here, we're going to have minus 500 pounds times 6 feet. And again, the minus sign is because if I sum moments about point A, the 500 pounds is producing clockwise moment, and I'm doing counterclockwise positive. And that's it. It's the only forces in this problem, so equals 0. So our moment is equal to, if I add this to the right, 3,000 foot-pounds. So I'll go ahead and write this up here. So our moment reaction, 3,000 foot-pounds or pound-feet, doesn't matter which. All right. Now to get the internal bending moments. So I don't need this anymore. I'm going to get rid of it. In order to get the internal bending moments, what we do is we draw a free body where we cut the system. So I'm just going to cut it kind of at an arbitrary location here. So what I'm going to do here is I'm going to draw a free body of this part of the system. Actually, I'm going to redraw that. I'm going to cut it here at an arbitrary location. Okay, let me move this somewhere. Actually, we'll move it right over here. All right, so what I'm going to do, I've cut the system. Now I'm going to draw a free body of the cut. So this AY, which I partially cut off, is still there. That's part of our system. This applied moment, the 3,000 foot-pounds, is still there. And now what I'm going to do is I'm going to add a shear and a bending moment, right, applied right at the cut. And I'm drawing them in their assumed positive directions. Right? Now what we can do is we can write both force and moment equations for this free body. Now let me go back here. I've got a pair of M's here. This was the moment applied at A. So let me put that. That was the reaction. This is the internal bending moment at an arbitrary location. Now it's important to realize, because that location is arbitrary, this is not a number. I'll call that a variable X. First equation we can write for this free body, sum of all forces, y direction equals 0. And that's going to be, remember this was AY, which is 500 pounds, minus the shear, and that's at equals 0. So it's pretty easy to find the shear force, 500 pounds. And now we can get the internal bending moment by writing the following equation, sum of all moments, and I'm going to do this about the left end, or point A, equals 0, counterclockwise positive. Now when we sum moments about A, AY goes right through this point, moment at A was plus 3,000 foot-pounds. All right, that's for this. Again, we calculated that earlier. The shear force creates negative moment about A. That's going to be minus the shear force value, which is 500 pounds, times the distance x. That's force times distance, minus because this force is creating clockwise moment about A. And then we got plus the internal bending moment there. And then equals 0. So it's just a matter now of solving for the internal moment. And what we get, let's see here, we'd have to add this to the right, 500, and I'm going to go ahead and leave the units out. I'm going to put NCU for note consistent units. That's going to be 500x added to the right, minus 3,000 pounds, foot-pounds. So you'll notice we got a constant shear and a linear moment. Now what I'm going to do is I'm going to go ahead and sketch these, draw graphs of these. I'm going to go ahead and do this. Now when you do shear moment diagrams, it's pretty customary to do them right along the length of the beam that you're analyzing. So I'm going to use this graph for my shear. Another graph here for the moment. Close enough, okay. Okay, so shear against x, moment against x. Now you'll notice that our shear ended up not being a function of x, so this is constant. And I'll just sketch that. All right, so constant out to that point at 500 pounds. All right. Next, the moment. Now this is a linear function. It's got a negative intercept with positive slope. And I'm going to do this just by plotting points. If x equals 0, the bending moment is negative 3,000. So I'm just going to put that there. Well, I'm running out of room here, but negative 3,000 foot-pounds. If x is equal to positive 6, right, if we run a 6 here, this is going to be 3,000, we get a 0. So this point in the graph is here, and these are connected linearly. I'm going to go ahead and connect them linearly. If I had more room, I would draw much larger graphs here, by the way, but boom. So that's what the bending moment looks like. Now, some things I'd like to point out. Both the shear and the moment have to match conditions at the endpoint. So let me take a look at this. So you'll notice that this 500-pound force is applied at the end of the beam, and actually let me talk about the left hand. Notice we have this 500-pound reaction up, and imagine doing a free body, just a sliver of this. And we have this 500-pound force up. That sliver would have to have a 500-pound force down, and down is the assumed positive direction. So this thing matches this, and it also matches on the right-hand side. If we imagine a free body of, imagine this 500 applied right to the end, and imagine a free body of just this small beam on the right. A free body of just this little piece would have to have a 500-pound shear force up. And up is the assumed positive direction for the right-hand side of the beam. So again, go back and look at sign convention for beams if you're not familiar with what I'm talking about. All right. Also notice that at the left-hand side of the beam, there is a 3,000 foot-pound bending moment. And you'll notice that this matches that. And you notice that there is no bending moment at the right-hand side of the beam. You'll notice that that goes to 0. So our graphs here match the conditions of the endpoints of our beam. Another thing I'd like to point out in this video, notice that if I differentiate this function dm dx, I'd get plus 500. And notice that the shear is 500. And that's not an accident. That's a relationship that always holds up. That the shear force is the position derivative of the bending moment. All right, this is a relationship that we'll use, more as time goes on. I usually use it as just a check to make sure my work is good. I usually do shear moment diagrams by what I call brute force method. Find the reactions, cut the beam in question at a location. Now here we only needed one cut, and that's because there were no changes in the applied load along this beam here. If, for example, I put another force here, we'd have to make 2 cuts, one on the left-hand side of it, one on the right-hand side of it. Or if I put a bending moment here, we would make 2 cuts. And again, I'll save that for other videos. The intention of this video was just to kind of get a flavor for how shear moment diagrams are done. I'll make other videos that require several cuts in the future. So I hope this video helps describe how to draw shear and bending moment diagrams. Have a great day.